All right, now finally, what if omega equals omega naught? So you saw when we were working with this, remember our original system was, where did it go? It was this, right? Harmonic oscillator, but driven with some driving frequency, forcing frequency, omega. And our original question was, how does it respond? How does the response depend on different choices of omega? And we came up with something, but it required assuming that omega is different from omega naught. That's because in the middle of our work, while we were trying to get a particular solution, we ended up with a system of equations where here B and C are our undetermined coefficients for the method of undetermined coefficients. And to proceed from here, we really needed to be able to divide by omega naught squared minus omega naught, minus omega. And that requires that omega not equal omega naught. Okay, what if omega does equal omega naught? Then here we just get a equals 0 and 0 equals 0. We cannot solve this if a is non-zero, which a is non-zero. So what do? Now the caveat applies, right? Our original differential equation was this. Omega naught x is a sine. And now I'm assuming omega equals omega naught. So instead of writing omega here, I'm going to write omega naught. Let me even put that in red. Now my usual guess of like trying to put in, b sine omega naught. So what would my usual guess be? B sine omega naught t plus c cosine omega naught t. This is not going to work because this is just going to be 0, right? L, the left-hand side operator, is just going to kill my guess. If I do what's suggested in this table here, where my choice of omega is omega naught, and I make a guess like this, L just kills it. So I can never find B and C that makes a sine omega naught t come out here. I'll always get 0 out here. So you see, this is the exact situation where we need the caveat. Okay, so let's use the caveat. Okay, so here's the caveat that I'm talking about, this thing in your textbook. And what it suggests is multiply by t, basically. It says multiply by the smallest power of t that works. Usually multiplying by t once is going to work. If it doesn't, it just means then try again. If that doesn't, then try again. But usually doing it once just works for textbook problems. So I'm going to multiply by t. So take my guess, my original guess, and multiply by t. So instead of b sine omega naught t plus c cosine omega naught t as my guess, I'm going to multiply all of this by t. So how about I put that in red, since that's caused by this red situation. So I'm multiplying the guess by t. Then I need to determine what is this. All right, that's going to be a big pain, because now you see I have to use the product rule to take the derivative here, right? Remember, L is a double derivative plus this. So that's going to be a big pain. But that's what I signed up for, right? So let's do it. That's what you signed up for too, by signing up for the course. So first derivative. So let's compute these individually. First, I'll work on this one. So how about first derivative? d dt of t sine omega naught t. That, by the product rule, that's sine omega naught t plus omega naught t cosine omega naught t. All right, now I need to take another derivative. So second derivative of this. That's minus omega naught cosine omega naught t. I don't know why I said minus. Okay, so just omega naught cosine omega naught t plus, and then I have to do the product rule again. And now I get, let's see, so one of the terms I get is just going to be, when I do the product rule to take the derivative of this, one of the terms is just going to be omega naught cosine omega naught t, right? So I get two of these actually. Okay, and then the other term is negative omega naught squared t sine omega naught t. All right, so that's the double derivative, which is one of the two things I need to, one of the two contributions to L of this thing. So now let me copy and paste a little bit. So L of this thing is, and yeah, please be patient. Sit through one of these calculations and then I'll speed through the other by pausing and skipping using Mathematica. So you should at least see one of these, I guess, to get a feel for what is involved. Okay, so it's this plus omega naught squared times what I've plugged in, so t sine omega naught t. And now let me combine like terms. So I see a cosine omega naught t here, but these are like terms. T sine omega naught t, t sine omega naught t. Oh, and they cancel. Huh. I actually wasn't expecting that. Well, that's nice. Okay. Oh wait, maybe I should have been expecting that. I think it's a part of the cancellation I mentioned in an earlier lecture where the bonus lecture where I described why the caveat tends to work. It's either that or related to that. Anyway, this is what we get, so great. Now, let me use Mathematica for the other one. And also watch this because it'll also show you how you can save yourself some effort using Mathematica. Okay, so now I'm going to try to compute L applied to this other term, t cosine omega naught t. So let me write it down first. L t cosine omega naught t equals, and then I'm going to try to compute this. And you know, I feel like a lot of things that are important are kind of off screen because all these boring calculations are here. So let me move the boring calculations off screen. And I don't know why I wrote that twice. There, now you can see. This is our guess. This is our L. Sorry. Okay, and we're working out these two things. Here's my Mathematica. Let me create a new one for this. Nah, let me just do this. Move this off screen. All right. So let's see. I've got t cosine omega naught t. And I just realized that from my previous work, omega naught is being used for something, so let me clear it. Okay, there. Now it's blue again. Okay, so t cosine omega naught t. Then I want to take its derivative twice. So how about, this is probably not the most efficient way, but this is the syntax that I know right now. If I do d it comma t, then that's the derivative of that with respect to t, and then I want to do it again, or do that with respect to t. I think there's a better syntax for that, but whatever. And I've created so many new lines here that you can't see the answer. Okay. So just forget this stuff for now. Okay, great. So that's the double derivative. Sorry. And then I also want to add omega naught squared times the same thing. So lots of copying and pasting. It's simplified nicely. So same kind of cancellation, 3 terms, and then it becomes 1 term. So it looks like I got minus 2 omega naught sine t omega naught. Great. Now I can write this equation down where, to help me determine the undetermined coefficients. And I'm happy that when I applied L, it didn't kill these things. So that's why the caveat helped. Applying L didn't kill these things. And it didn't give me annoying t sine omega t, t cosine omega t terms. Those canceled. That's the caveat working. Okay, so b times 2 omega naught cosine omega naught t. So what I'm writing, let me be clear about why I'm writing this. What I'm writing is this, right? So I'm writing this. This is b times the result of applying L to this part, which I computed here, plus c times the result of applying L to this part, to this, which I computed here. So minus 2 omega naught sine omega naught t. Okay, and what do I want this to equal? So want equals, we'll go back to the original differential equation. It was this. I want to get a sine omega naught t. And now looks like I have a hope of doing that. Since I'm not seeing that annoying omega minus omega naught multiplied by things. That would have been 0, right? Here, in this particular case. So match things up. So I've got this matched up with this. And that is just going to end up being 0. So let's just write down the system of equations. We have, for our second equation, maybe, so you can view this as plus 0 cosine omega naught t. So this is, let me use blue for that one. So this is getting matched up with 0, right? So my second equation, the blue one, is 0 equals 2 omega naught b. And the first equation, the green one, is a equals negative 2 omega naught c. Okay, so the solution is b equals 0, and c equals negative a over 2 omega naught. Which, again, you could say, oh, are you dividing by 0? Is omega naught 0? No, omega naught is not 0. If omega naught were 0, what are we even doing, right? Then you're not even looking at a harmonic oscillator. You're just looking at something with no, well, then I guess K is, there's no restoring force anymore. It's just a free particle rather than a harmonic oscillator. Okay, so nope trouble here. All right, so we've got our final solution. Our final solution, so the general solution will be x of t equals c1 cosine omega naught t plus c2 sine omega naught t. That's just like before, plus the particular solution, which is c. So this is kind of interesting. It's on the right hand side here we have a sine type of thing, not a cosine thing, a sine thing. And back in the case omega not equal to omega naught, remember what we got? Let me flip back to that case. We got for our particular solution something with a sine. So sine for the forcing function, sine showing up in the particular solution. But I think it's really interesting that in this situation where omega does equal omega naught, we ended up with a cosine in our, still sine in our forcing function, but we ended up with a cosine, right? We ended up with b equals 0 and c equals, so b equals 0 and c equals this thing. So we've got, yeah, this with the c filled in. So t cosine omega naught t. T cosine omega naught t. I just think that's so interesting that we got cosine there. And then this is negative a over 2 omega naught. So yeah, compare what we got. Here, for our particular solution, there's a cosine, and then there's a over 2 omega naught. And that's apparently what the system is trying to do when, where did it go? Where did it go? There it is. This was our general solution back when we were assuming omega does not equal omega naught. So you see, if you try to make omega be very close to omega naught, then this is nonsense because you're dividing by 0. But apparently what it ends up doing when you try to force it, it still has a response, it still does something. What it does is this. So this t pops up here, and the sine becomes a cosine, and then this becomes, the thing in front becomes this. This is very interesting how that behaves. So let's try the same thing we did back here, where we tried these specific initial conditions. Let's put those in and then see what we get for the plot. Okay, and I will not make you sit through the whole calculation of what C1 and C2 are again. I think it's healthy to show calculations to a certain extent, and it's healthy to just let the computer do them to a great extent. So let's just define x of t equals, and then I'm going to type in this stuff. All right, and I've typed it in, but I see the a here is black, which suggests that it is using previous values that I had put in. So clear it out there. There we go. Okay, so now I've typed in this whole thing, and the reason to do that is so that I can evaluate x of 0. Well, that's C1. Okay, big surprise. But I'm also interested in evaluating x prime of 0. And I want to set both of those equal to 0. That's the initial conditions I'm interested in. So there's these two. Then what I'm going to do actually is put these in a list and solve this system for C1, C2. Okay, so C1 is 0, C2 is this, a over 2 omega naught squared. So this leads to x of t equals, this term dies, and a over 2 omega naught squared times the sine of omega naught t. Well, this is also a over 2 omega naught squared, so let me just merge these, minus t cosine omega naught t. Okay, so pretty similar to what we got before, but actually not similar at all. Where did it go? Before, when we put in those initial conditions of starting from rest and starting from equilibrium and at rest, before when we put those initial conditions, we got this. So it's like difference of signs. And look here, I've got a sine and then a t times cosine. Look at this. So the amplitude of this term just grows linearly in time, right? So if I were to like forget about this term and just focus on this one will dominate eventually, right? Basically, I've got, this is the kind of envelope in which my oscillation lives. So I just expect it to, the amplitude to grow forever. As t grows, the amplitude just grows. This phenomenon is called pure resonance. Pure resonance. Part of pure is, I think part of the word pure is undamped. So we haven't introduced damping. So everything we've done here is actually kind of unrealistic. Kind of extremely unrealistic because the damping is not there. On your homework, you will put in the damping. Okay, so let's finally plot this. So over here, I'm going to go back to choosing omega not equals 1 and a equals 1. And this was our plot for the different choices of omega, but our plot fails at exactly omega equals 1, although it seems to show close to the right behaviors. But if I let the plot run for long enough and for large enough, let's maybe go 100 to 100, you can see that it doesn't grow forever. So let me run it for long enough. I don't know, 48. It's still eventually, it's growing, but it's still eventually going to come back down. It's just it's a beating, but with a long period. Now, so this was our old thing. Now let's put in this one. So let me just copy this put it here. And let's see, a over 2 omega naught now, 2 omega naught, squared. And there's nothing to manipulate now, right? I'm actually looking at a specific case where omega is fixed in the middle of this bar, which is omega equals 1. There's nothing to manipulate anymore. Yeah, just trying to see what to change. Looks like I need to multiply by t, and this is a cosine. And I think that's everything, except now this is an omega naught here. There's no more omega. Omega equals omega naught. And this is what we get. So no matter how far out I run time, the amplitude is just going to keep growing like that. All right, so this is pure resonance. This is the note that breaks the wine glass, basically, is omega equals omega naught. But there's this unrealistic aspect, which is, of course, you can try to keep adding energy to the system by driving it at just the right frequency, but there's a limit. The system is only going to, a real system will dissipate energy as well, right? Be it a swinging pendulum or a mass on a spring or a circuit with a capacitor and an inductor and a voltage source. It's going to dissipate energy somewhere, even if you don't stick a resistor in there. There's some resistance. And a realistic version of this would include damping. So in our original setup, let me go here. In our original setup here, we really should add another term here, a damping term. And then we can ask this very same question with a damping term there. So that will be on your homework, and I'm going to make some comments about that in the next video.